What's up? Matt here. I just wanted to put out a kind of follow-up redo of a video I put out a while ago about this cartoon shader that you see. It's pretty cool, and it still works, and it's totally a valid way to do this Toon shader. There's a couple changes to it, and more importantly, I found, I think, a better way of accomplishing both of the effects. There's two post-processing effects here. There's the outline, and then there's a cell shader. I'm not necessarily going to go over that concept again, but we're going to make a new one here. So, first of all, let me give some credit where it's due. I found a lot of these. I haven't invented hardly any of this. I've made a couple tweaks to some stuff, but the new edge detector is from an Unreal Engine training stream with the tech artist Tom Shannon at Epic. And he goes through how to do this edge detector and also a different kind of cell shader, a kind of third option. I'm not going to use that one. I'm going to use this forum post by name. I'm going to butcher Thura Oo, I think is the username here. This is great. I highly recommend it. Better than the one I showed you before. They're all just different approaches. And we're going to be going over how these effects are achieved, especially the edge detector. It's a method called Kernel Convolution, and I'll link to a playlist by the channel Computer File about how blurs and filters and Kernel Convolution works by, I think it's Professor Mike Brown at Nottingham, which is really great, really informative. You don't need it to be able to do any of this stuff, but if you really want to understand post-processing effects, it's a great watch. And another series about graphics engines in general by John Chapman, same channel. He kind of goes into triangle rendering and depth buffers and the kind of structure of a graphics engine, which is pretty great. Once again, you don't need to see it, but it's a good resource. And also this blog post by another name I'm going to butcher, Utkarsh Sinha, about the two methods here of edge detection. The old one that I was using was the Laplacian Filter, and we're going to move to a Sobel Operator. Both of these are this kernel convolution stuff. Okay, so I'm starting with the old project. I've actually got two post-process volumes, which is what you need to make a post-processing effect work, and they're both set to be unbounded. By default, it will just apply the effect to things in the post-process volume, but you can set this little check marks to be infinite extent, and it will apply globally. And you can have multiple post-process volumes, both active, and they'll both apply their effects. I've currently got this one disabled. This is just the default set of effects, and this is the last video's cartoon shader. So let me quickly run through like the tiniest quick improvement to this. You notice how if I hit play, especially if I full screen it, you notice some kind of jitteriness on a lot of the edges here. Kind of apparent on the stairs, and even more apparent if you pulled in like a landscape mesh or something. That's a really easy problem to solve just by going into the material here, which I'm not going to rebuild today, and changing the blendable location to happen before tone mapping. Unreal and all graphics engines really run in a couple of passes. And you can specify where in the pipeline you want your post-processing effect to happen. Before tone mapping is a little bit more expensive than happening before translucency, or sorry, a little less expensive. The earlier in the pipeline it happens, the more expensive it's going to be. Tone mapping is the kind of internal suite of post-processing effects. Things like anti-aliasing, I think things like bloom and depth of field are in there. But the thing that's causing this jitter is temporal anti-aliasing, which is something Unreal uses to smooth out edges by kind of looking over a couple of frames at the edges. The problem being that if we're trying to draw lines on those edges, then you get this jitter effect. So by applying our effect before that one, it's going to just totally remove that jitter. So we set it to happen before tone mapping, we hit apply, and boom, totally gone. Totally clean lines. It's already 100 times better. The other disadvantage of this Laplacian filter versus the Sobel one is that it's a little more prone to noise. Usually in a straight image you would apply like a Gaussian blur beforehand to remove it, but you notice how these lines are not necessarily clean. You get some, it goes back and forth between applying and not applying the effect. This is extremely apparent on landscape meshes, that it kind of has a lot of edges applied to it where they don't need to be, and it's most annoying if you're kind of moving back and forth because it'll kind of reintroduce some of that jitter. So the method I'm going to show you today, the Sobel operator, is just a different approach, gives you a different set of lines, but I think it's a little bit simpler, and I think in the end it's a little bit cleaner as well. So let's talk a little bit about what kernel convolution is, right? So I'm going to pull up my favorite drawing tool and draw us a beautiful starting image. So we have a starting image, and any kind of filter or blur post-processing effect is going to take this image and iterate over every pixel in it to try to produce a second image. The way we do this with kernel convolution is to take kind of this little miniature grid called a kernel and put the center pixel on the one that we are looking at, and then based on the surrounding pixels we're going to do some operation to the center one. This doesn't have to be 3 by 3. A blur effect might be 7 by 7 or 9 by 9 or even bigger. But the Sobel and the Laplacian are this size. So the Laplacian, for example, I think uses like 1s and a -4 in the middle. And basically you take two images, you usually will convert them to grayscale. In the Laplacian filter, you'd probably run a Gaussian blur over the image first just to remove some noise, and then you iterate over this, and based on if there's a high change in intensity from one pixel to the next, it'll define that as an edge. The Laplacian filter almost acts as a second derivative, if you know what that is, of this intensity. So if we had like, if we had an intensity that went like this, and this is outlined in this blog post, high intensity versus, say, one dimension across the image, then its first derivative, I'll make a new one here, is going to look a little something like this, where we get a lot of change. And the second derivative, which is what the Laplacian filter is going to do, is going to kind of go up and then under and then back up. And this is handy because this 0 point is our edge, and it gives us some information about what's happening on either side of the edge by that direction. Pretty cool. The Sobel operator actually runs two kernels, one to check for horizontal edges and one to check for vertical edges. And it produces the similar kind of output with a little bit less information about what's happening on either side of the edge. But in our case, we don't actually need that information. So that's the one we're going to run with. Now the other difference between a regular image processing effect and doing it in post-processing in Unreal is that Unreal Engine gives us a lot of access to information you don't have if this was just an image or a movie. We don't have to deal with just grayscale intensity. We can actually get access to the depth and the normal vectors of all the pixels, and so we can actually find the real edges in the image. So you can think about different ways, different kind of channels you might look at for edges, and I'll spare you the time. There are two ways that we're going to do it. One is by comparing the depth of neighboring pixels. This pixel is much closer to the camera than this pixel, and that marks an edge. That leaves out some stuff. These edges of the staircase have a pretty defined edge, but the actual difference in distance to the camera between these pixels is not very big, and so it's not going to pick those up, or these kind of inside edges, very cleanly. And so we're going to do a second pass with the normal vectors, because there's a big difference between the normal vector of this pixel and the normal vector of this pixel. So let's just get started. I'm going to take my old post-processing volume and or my new one and enable it, and my old one and disable it, and you notice that this gets me the regular old scene. The only thing I've done, this is a third-person template, and I changed the words on the floor, and I disabled motion blur because I don't like it. So to get started, let's just make a new material. And I'm going to call this PP Sobel, because it's a Sobel edge detector. And the material domain isn't a surface, it's not a decal, it is a post-process effect, which removes everything except the emissive color node, and it also gives us access in this scene texture node to all of the data in the graphics buffer, the G buffer. Not everything. scene color is illegal because this is not a surface material. But there are a lot of channels in here that we now have access to. Scene depth, diffuse color. All of these hold different information about the scene. So if I go into my post-processing effect and I add an element to this post-processing materials array and asset reference, I can add this, and actually I'm going to go ahead and I'm going to make a material instance because we're going to be making some parameters. You notice that this diffuse color node is just like the color of the material without any lighting applied. That's useful information. It gives us just the straight color of every pixel before any of the effects are applied. You can do world normal. We're actually going to be using world normal, and this gives you the direction of the surface that the pixel's on. Pretty handy stuff. You can have all kinds of things: specular, metallic, subsurface, roughness, ambient occlusion. You've even got this custom stencil, which we're going to look at a little later. Another important one you need to know is post-process input 0. If I show you what this looks like, it looks like nothing, because it's actually the raw input into our post-processing effect, post-process input. So this is how we're going to add the regular scene information back in. It's post-process input 0. And I'll also go ahead and show you what depth looks like. It's not going to work at the beginning because it's like mapped from 0 to 1. And so if I divide by some number, 200 maybe, and then I use this frac node, which is going to make it roll over every time it gets to the max, you'll be able to visualize this a little better. Little confusing to look at. Skybox is a little weird, but basically from 0 to 1, this gets you the depth of each pixel. So for example, dark would be closer and light would be farther away, and then it rolls back over. Anyway, so that's just information about how far each pixel is from the camera. So, getting rid of that. Let's build one half of the Sobel operator with the depth information. Remember, we're using the depth and we're using the normal information. What we need to do is take a pixel and then compare it with the pixels to the left, to the right, up, and down. So, this is pretty easy. I've already got our center pixel. To get the one to the right is a little complicated, not too bad. We're going to take a texture coordinate. And this is just the coordinates of the pixel we're looking at. If I plug this in here, it would have no effect. And we're going to take that, and we're going to plug it into another scene depth node. This is also going to be the center. We're going to take the center, and we're going to take not its size, but its inverted size. Its size is straight how big the pixel is, and its inverted size is the fractional size, the percentage size over the whole image of how big this pixel is. So we're going to take one pixel's size, and we're going to multiply that, because this is a two-dimensional size, by a vector 2. Where one of these is going to be the x-axis and one is going to be the y-axis. And so what we want is to go one pixel's length to the right. In this case, we're going to start with the right pixel. So we go 1 on the x-axis, and 1 times this percentage size is going to be 1 pixel length, which we're going to add back in to our current coordinates. And that gets us the texture coordinate of the pixel to the right. And we're going to go 0 on the y-axis. Pretty simple. And we're going to use that as UVs for the right pixel. So now the output of this node is the depth of the pixel to the right of the one we're currently looking at. And finally, the way the Sobel operator works is we're going to take the center pixel, and we're going to take the pixel to the right of the center pixel, and we're going to subtract them. Simple enough. And the way this works, if I plug it into emissive color, is that we should get some lines. Some lines specifically on the left side of objects. Because anything that goes from far to close is going to get a line, and it only applies on the left side, because we've only looked at one edge. And the way we look at the other edges is just to straight copy and paste this a couple more times just to make a huge mess. And we're going to do the left and the bottom and the top. And so the left pixel is just the same thing, but -1 instead of 0. Remember that we start at the top left, and positive values go to the right and go down. And so the bottom pixel is actually not -1, but it is 0 on the x and 1 on the y. And the top pixel is 0 on the x and -1 on the y. And if we simply add every one of these together, and one more add right in the middle, we should get some lines. Wow, amazing. So these are lines based on the depth of pixels. You notice we're missing some stuff. I didn't get this edge or this edge or this edge because the actual distance from the camera of these pixels doesn't change very much. It only finds things that have a difference in distance from the camera. So let's go ahead and add that in. It's actually much easier than you might think. We're going to just take this whole thing and copy paste it again and just make a huge big old mess. Except that instead of scene depth this time, we're going to use, and I'm going to hold Control to select all these at once, we're going to use world normal. And this is going to give us a different effect. I'm actually going to unplug this, and I'm going to plug this one in. And what we should see is some strange colors. Now, one thing I'm going to do just to keep things in check here is this actually outputs four numbers. It's a 4-dimensional value. It gets red, green, blue, and alpha. And for the scene depth, we really only need a grayscale value. And so what we're going to do is actually mask this. And I should have done this before because now I'm going to have to sit here and copy paste a bunch of times. But it's going to be okay. It won't take long. So we need one there, 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 there. Plug all of you in. And this is just going to prevent us from kind of throwing too much information at it. This is going to be more apparent why I'm doing this on the normal based, because we actually want more than one channel on that normal vector based one. We're going to do the same thing here, but the mask, instead of using one channel, is actually going to use R, G, and B. And I apologize for not getting this the first time. But we want all three colors, all three dimensions of that normal. And there we go. And one thing we're also going to do is you could use this color information. It gives you the kind of color based on the two normal vectors it's comparing. So you could do different colors or different thicknesses of line based on what angle it's at, and that could be pretty cool. We're just going to use the same as before. We just want these lines to be white. And the way they showed this in the stream was using the add components node. And because we're using RGB, we have 3 components, and we're just going to add them all up and output it straight to the emissive color, same as before. Okay, more lines, and you see that we get things like this inside edge very nicely, where we didn't before. It's not perfect. And another thing I should note is that this component, this normal-based component, will not work in VR. And the reason is that VR is going to use the forward renderer, and the forward renderer does not give you access to this world normal channel, I don't believe. So you're going to have to make do with depth-based lines in VR, although if you're doing this in VR, you may want to consider, these are not expensive shaders by any means. 63 instructions down here is less than most materials you're going to find, but it is enough in VR that you may consider writing your own, digging into the HLSL stuff. No big deal. So we're also going to want to combine these together. And you could just add them. The way they did it in the stream I really liked, which is to use the max node. And this way, if there are, if both the depth and the normal produce an edge on the same area, then it will just take whichever one was brighter. And now we get all of our edges all the time. Pretty good. We might also want to do a couple more little things to have control here. We're going to want to parameterize kind of how thick these edges are and how defined an edge needs to be before you have it. So the way we're going to do this is by at each of these outputs, we're going to use a multiply node and we're going to use a power node. And I get the multiply by holding M and clicking. And we're going to take two scalar parameters by holding S. And because this is the normal, I'm going to call this normal line multi and normal line bias. Both of these with a default value of 1. And I'm going to copy these nodes and I'm just going to paste them up here with Control W for duplicate. And I'm going to rename these because they're on the depth channel to depth line multi depth line bias. Okay. That should help out. And lastly, I'm going to go ahead, well, I could go ahead and add the regular scene color back in, but it'll be easier to tweak the lines beforehand. Although you're going to want to not make decisions about how thick and how defined the lines are at this point, because adding the scene color back in is going to change things a little bit. But just to show you what it does, I believe I'm using this instance already, and if I override some of these, you notice that these lines get a little more defined when I change the bias or the multiplier. I found 1.3 works pretty well on both of these. And the bias is going to change how defined a line needs to be before it's added to the scene. So that's an interesting effect. You can kind of get an almost stippled dithering sort of look. I found leaving these at 1 is pretty okay. All right, now let's finally add that regular scene color back in. And I'm going to do that by using a lerp, linearly interpolate. And one thing you might know if you have used the linearly interpolate before is that when you're plugging the alpha in, you have to clamp it. It won't clamp it automatically, and if it flows over 1, then it's going to reset and give you some weird results. So we're going to take this and clamp it between 0 and 1. And that's the alpha. Black is 0, white is 1. Full alpha means we're going to get our line, and the way we're going to get the color is with the scene texture post-process input 0. If I plug this straight in, and I plug in, I'm going to use a vector parameter. This is going to be the line color. We'll leave it at black for now, but it's going to throw me an error, I believe, if I plug this into emissive color. Because this is a vector 4, and this is a vector, or rather the alpha is, I believe, 3 channels. Or maybe this one's 3 channels. But regardless, we're going to need to mask this. Component mask to R, G, and B. There we go. And this actually should give me some lines. Now you notice we get the same jitter as before, and that's the same temporal anti-aliasing problem that's solved by going in and putting this to happen either before tone mapping or before translucency. If you're using translucency, which is not going to be particularly effective when you have the cell shader, then you may want to have it happen before or after. And there's our effect with just an outline. Looks a little better on defined edges like this. You also notice it's affecting the skybox. We're going to fix that after we do the cell shader, because I'll show you how we fix it in the cell shader, and then we'll just copy paste it. And you can tweak the line thickness, you can tweak the colors, but that is our edge detection filter, pretty much. Let's do the cell shader. It'll be a little easier, I promise. I'm going to make a new material. This is going to be pp cell new. And I'm going to go ahead and I'm going to make a material instance. Before I get too far, I'm going to open it up and set it to post-process so that I'm allowed to go into this and to add an element as an asset reference as my new cell shader. And it's doing a whole lot of nothing at the beginning, because we are not plugging our scene texture back in. Dope, I messed something up. Oh, you're not allowed to use scene color. Post-process input. Okay, now we got our lines back. Okay, so the method I showed before of doing the cell shader used this kind of lookup texture, which is a 1 by 128 pixel, and it kind of finds the lighting data and maps it onto this so that anything shaded up to a certain point is just unshaded, and then anything past that is shaded with the same color. This doesn't give you a lot of control, especially over what color the shaded is and what kind of thresholds you use. A cell shader is going to be really difficult in a game or a scene that that switches between a kind of darker and lighter environment, and so you're going to want to be able to tweak that on the fly using just material parameters. So I like this method a little bit better. So first, we actually need to get access to the lighting information of the scene. I'm going to unplug this, and the way we're going to do that is using this and using the diffuse color. Diffuse color, if you remember, was just color without lighting information. So this one doesn't have lighting information, and this one does. And a method we can use to get just the lighting information is to divide. And before we do that, actually, I'm going to desaturate, which is going to make these into grayscale. I'll show you here what exactly this does. It pulls it into grayscale, because we only want to compare the intensity of the light, not the color effects on the material. So if we divide one by the other, and then we plug this in, you'll see that we really just have information about how lit each pixel is. This is all pretty blown out at the moment. Part of that reason is in my post-process volume. There's a couple things we're going to want to change. We're going to want to take auto exposure and set the min and max brightness to the same value. Auto exposure means that if you're in a light room or in the sun versus in a darkened room, it kind of will adjust the exposure of the scene to compensate, and the cell shader is going to mess that up pretty badly. And we're also going to want to take bloom and make sure its intensity is set at 0. And this is going to give us a little bit better. So this is purely shadow information. Excellent. Now that we have access to that lighting data, we're going to want to get what tint we're going to add based on whether we're in a light or dark area. And we're going to do that once again with diffuse color. We'll start with the lit areas. We're going to take diffuse color, and we're once again going to take post-process input 0, and I'm going to make a scalar parameter. And this is going to be called light blend amount, because it's how much of the original post-process effects we're going to incorporate into the scene. If you leave this at 0, you'll get the straight, flat, cell-shaded look, which may be what you're going for. It doesn't work quite as well as you might think for moving images. I'd like to leave this at 1. I'm going to let all of the post-process stuff back into the scene, and we're just going to kind of band the lighting to get that cell-shaded look. But you can tweak this parameter as you go. We're going to multiply these together. That's going to influence how much of this post-process input gets back into the scene. And we're going to add that to the diffuse color. And then finally, we're going to take the output of that and multiply it again by our color. And our color is something we can define on the fly, not just on the fly, but as a parameter. You can change it in the middle of your scene, which means that if you enter a darker area, you can change what the effect is on the shadows. And to make this multiply correctly, we're actually going to append the number 0. I get a constant by just holding the 1 key and clicking. And I also get a vector parameter by holding V and clicking. So multiply those together, and this is our light tint. And we're going to take this and just copy paste it exactly the same, except that instead of white, this is going to be our shaded amount. I'm going to set it to 0.5, 0.5, 0.5. Dope, I messed something up. No, that's fine. Okay. All right. So now we need to decide. We need to decide if the amount of shading is greater than some threshold, then we need to apply the dark shadow. Otherwise, we need to apply nothing. And the way to do that is with an if statement, which I get by holding I. And this is going to say you take two inputs, A and B, and you've got some output if A is greater than or equal to or less than B. So our actual numbers we're comparing are this lighting information and some scalar parameter. This is just going to be called darkness factor or darkness threshold. I'm going to default it to 0.5, and it's going to go between 0 and 1. Okay. And then, if our shading is bright enough, the white areas of the scene, we're going to use nothing. Otherwise, we're going to use this shaded effect. And we can output that right now, and it should do something. We get cell shading. Look at that. You get some jankiness over here, and depending on exactly what you want, I don't know, that might be an effect you want to go for, but it's kind of important that you set this once again to happen before tone mapping, or before translucency if you want, just to reduce that. And already we've got a pretty nice looking cell shader. Now, you don't really want to apply the cell shader to the skybox. This isn't doing anything because the skybox here is emissive, but it is messing with the sun. And it'll mess with your background depending on what you've got set up. So, and we're also going to want to do the same thing to keep the lines from happening on the skybox. So we're going to want to add those back in. And the way we do that is we're just going to take scene depth. I'm going to Control W to duplicate and set this one to scene depth. And we want to check if it's farther away than a certain point. The material on the forum just uses 1,000,000. So we're going to divide by 1 and 1, 2, 3, 4, 5 zeros. And make that grayscale just to get it as one number. And then we're going to take another if and compare that to the number 1. And so basically if it is greater than 1, it means we're farther away than 1,000,000 units, and we need to not apply this effect. Otherwise we do. So not applying the effect would mean that we're just plugging the regular scene input in, and applying it would mean that we just take that output and put it in. Boom. There we go. You don't notice anything different here, but that's just the nature of how this skybox works. And like I said before, we can actually copy this, Control C, and we're going to use the same thing in here to prevent that from messing with the skybox. One thing you'll notice, if I just do this, this is our post process, is that it will not work. It doesn't like comparing these. What we actually have to do is take this mask, and we have to mask it to RGB, and we have to mask this to RGB. One moment here. Oops, excuse me, I still need this, because we're using this as A, and oh no, I've got this the other way around. We're actually taking this input, and this is if we're closer than 5,000,000 units. There we go. Just making sure everything is the right number of numbers, the right vector length. And there we go. We have removed the lines from our skybox. Beautiful. Now this is pretty much done. There's one more thing I'm going to show you how to add, but this is how it is. A couple notes about the cell shader. For the most part, it's going to break specularity and metallic information as well as roughness information, you're just going to want to zero those out and use flat colors. This mannequin model is pretty specular, and it kind of works. It doesn't look too bad, but it's going to misinterpret specular, metallic, and roughness information as lighting information, and so you may get some strange shadowing effects. It's also going to mess with emissive color, and it's going to mess with translucency. You can still use those objects in the scene, you just won't be able to apply the cell shader, or it will look funny if you do. So the question then is, how do I selectively apply the cell shader to only objects that I want? Or how do I just apply the edge filter to objects that I want? And the answer is something fancy called the custom depth buffer, or the custom depth stencil. And in objects, you can enable this by setting it to render custom depth pass. And you can actually set its custom depth stencil value. And this is something you can read in the post-processing effect. In the cell shader, we're going to add one more component here, and that's going to be the ability to read that custom depth information and determine by whether an object has it enabled or not, or whether that object has it set to a certain value or not. If you had multiple depth stencils you wanted to use, we're going to apply or not apply this post-processing effect. So we're going to use scene depth as well as custom depth. This is the custom depth stencil value. And the regular post-process input. And let's see, I need a mask. I'm going to take this and mask just to get one channel on both the scene depth and the custom depth. And one last if statement. And basically, we're going to check the scene depth versus the custom depth. And we're going to apply this if it's greater, and we're going to do nothing if it's less than. Simple as that. You can use a different condition here. You could use a constant. Oops, not a 2 vector, but a constant. And you could use 1 or 2, or check if this depth stencil value is equal to something. So that, say, setting this to 1 would opt into the cell shader, or setting it to anything less than 2 would opt into the cell shader, so that you could have it apply just the cell shader but not the edge detector or otherwise. In this case, these two effects are going to go together basically all the time, and so we're going to use them or not use them, basically. And we should be able to do the same thing in the Sobel. And apply this here, and apply that there. Oops, except that I need to mask this to RGB. Okay, and now what you'll notice is that, nothing's happening except to this object, which has had that depth stencil applied. So if I take most of the objects in the scene here, and I can go to rendering, except they have different parameters, so I need to deselect one. Oh goodness, you can definitely multi-select here. So down in rendering, I can set them to use custom depth pass, and they will, bang, use the cell shader. And the way I prefer to do this, honestly, is to disable this by default, and then to, in the cell shader, switch these two nodes around. I'm going to hold Control to drag this. And this is just going to flip them so that you have to opt out of the shader. And now we get it unless we don't ask for it. Okay. So in essence, that's another way, a way that I kind of prefer, because it gives you a little more control of doing this Toon shader. Once again, this mannequin looks a little silly because he's got all that specular information, but we don't have the same problems with the cell shader as before, like the kind of weirdness around adding and merging shadows together. And the edges look a little cleaner, especially on big organic looking meshes, and you've got a lot more control. I'm going to check one more thing with you, and if that doesn't work, I'm just going to cut here. But I'd like a way to actually adjust the thickness of these lines. And I think the way to do that is to take this Sobel operator, and currently we're checking 1 pixel out. Let me just run an experiment. We're doing it live. Set this to -2 and 2 and -2. So this is checking 2 pixels out instead of 1. And I kind of just want to see what that'll do. Yeah, look at that. Look at that. Now that only did it with the normal, or with the depth lines, not the normal lines. So what I'm actually going to do then is, in the Sobel, if you want control over not just the this controls kind of whether you have thinner and thicker lines or just thick lines, and this will control how defined an edge needs to be before it even gets drawn. What I can do is make all these, put these back to 1. And I can multiply them all. Oops, that is not what I wanted. Hold M to get a multiply node. I'm going to get a couple of these, and I'm going to add another scalar parameter. And this is just going to be called, well, I might as well split it into 2, right? We'll get depth, line, thickness. And that's going to default to 1. And we're actually going to multiply those. You could just duplicate this parameter, but we've made enough of a mess that I'm just going to leave it as the spaghetti that it is, and then plug this in where all these went. And the same with the depth here. Pull all these out, add some multiply nodes, add another scalar parameter. This is going to be called normal line thickness. Defaulted to 1. And we're going to multiply all of them by that. And realistically, I should be truncating this value because it doesn't make sense to go over 1.5 pixels. But we're not going to bother with that at the moment. If there is enough interest, I might try to store some finished versions of these blueprints somewhere for download. I don't know that it's not mine, so I'm not going to put it on the marketplace, but okay. So now we should have those parameters. I'm actually just going to go ahead and kind of make a normal lines like category and a depth lines category. And I can take these, put them in the depth lines. I can take these, put them in the normal lines. Apply, save the cell shader. I might as well save the old one too. And I'm going to pull up the Sobel instance and the cell shader instance. Pull them over here, and I'm going to override all these things. Let's check it out. So if I like crank this, ooh, that's pretty cool. You notice that it only happens once I actually cross a threshold, so really this should only be allowed to be an integer value, but if you wanted thicker lines, you can set these to 2 or 3 or something, and you can play with the thresholds and all of that jazz. But this is how I'm doing it, and it's relatively efficient. It's easily, it gives you a high amount of control, and it looks pretty nice. So that's that. Thanks for sticking with this very, very long explanation. Check out the links below, I suppose, and come back later. I might do some more cool stuff, who knows.